So today we'll explore 6 more devices that have p-n junction type characteristics and can be used in several different ways. Okay. Of the 6 items that we're going to talk about, 2 of them need a little bit more clarification. The first is the tunnel diode, and the second one is the gun effect. They both depend on the quantum mechanics of atoms. Okay, the quantum mechanics is a field of physics that explores how the atomic structure can be explained mathematically. Right, and mathematically, the key thing about this is that when particles get very small, okay, they have what we call a duality of nature. The duality is basically that they have mass properties, and the other is that they have wave-like properties. Okay, if you're familiar with light, you know that light is electromagnetic radiation, and it has a wavelength. Okay, so we think, okay, all we need to know about light is that it's a wavelength, and it has its electromagnetic waves. Okay, but it also has mass properties. Okay, we talk about photons. Photons have mass. Okay, so photons of light are the mass property of a light. So light is both mass and a wave. Okay. Similarly, an electron also has a certain mass associated with it, but we've also done experiments that show that it definitely has wave-like properties. Okay, it behaves very much the same as light does. Okay, but at a totally different wavelength. Right. The mass properties of the electron are easy to calculate from the original Bohr model of the atom, where we've got electrons that are running around the nucleus of the atom being positively charged and the electron being negatively charged. So we know that electrons have a negative charge associated with them, but they are also wave-like. Well, if they're wave-like, then they have electromagnetic radiation associated with them. So the electron then is pictured in quantum mechanics as a wave-like entity. All right. What does that mean? Well, when we solve the wave equation for an electron that's constrained to be in a certain potential field, okay, think of your sci-fi pictures where you're flying in space and you meet a barrier. Okay, the same thing electronically down at the atomic level. The barrier, though, in this case, is a potential energy barrier. It has to mount the electron in order to go through that barrier, has to come up in energy, has to gain some energy to barrel through that barrier. All right. However, when you apply the wave equations to the electron and have that electron placed inside a box of surrounding a potential energy barrier, we found out that the solution to that is that there is a probability that that electron can be outside those boundaries. How does it get there? Don't know. Okay, but the solution, the mathematical solution, is that it can exist outside those boundaries, even if it doesn't have the maximum power to surmount that boundary. The effect is called tunneling. Right? So we call that tunneling because the electron has a probability of being outside that boundary. Okay, can break through that boundary. So in the case of a tunnel diode, actually, the boundary is the p-n junction itself. Okay, the p-n junction is envisioned as a ramp of where the electron has to gain a certain amount of energy to float into the adjacent region. All right. So our picture of the valence and conduction band applies here, and the tunneling then occurs through that p-n junction. Okay, and we'll go over that as step by step. In the case of the gun effect is one in which the electron seems to be in one of two different states. Okay, because in reality there is more than one conduction band. Okay, there are multiple conduction bands that could happen, and they differ because the wavelength can differ. Okay, so if it's in conduction band 1, it has a certain wavelength. If it moves to conduction band 2, it has to change its wavelength to a different value. So the gun effect considers that in the case of a gallium arsenide material, gallium arsenide being a semiconducting material that's used a lot in LEDs, light emitting diodes, and lasers as well. Okay. So that's the story behind the two different devices that really should have an understanding of the band theory of semiconductors of solids. Okay. So if you have any questions or if you're all confused, give me a call. I will write up a white paper to clarify it a little bit better. But it does take a lot of math involved, and I'm not sure you want to get involved with the math. All right. So, but I will explain it as best I can. And also, you can also look it up. You can Google band theory, and you'll get a lot of information on that. So good luck, and call me if you need me.